Good morning to you all. I welcome you all to this 4-week MOOC course on stochastic processing. The prerequisite for the stochastic processing is fundamentals of probability theory and in specific for a electronics and communication engineering student, the subject of stochastic processing is needed for analysis of analog, digital, and wireless communication systems, wherein the noise, the unwanted component, will be added to the signal either in wired communication or in wireless communication system is random in nature. So the best possible solution to a communication engineer is that they should nullify or reduce the amount of noise present in the signal. So here the discussion starts with the fundamentals of probability theory. So an experiment will be performed. The possible outcomes of the experiment, and a very interesting statement here is that for a random experiment, the set of all possible outcomes is known before the experiment. If I consider a tossing of a coin, I know the two possible outcomes are head and tail, but we cannot expect what will be the outcome. So that is given here with two beautiful sentences. The set of all possible outcomes is known before the experiment, but the outcome of experiment is not known in advance. So there is a point sorry that's the point of discussion in this subject. So next one. So if a random experiment is performed, the all possible outcomes of that experiment is considered as a sample space. So if you consider an experiment example here, tossing a coin twice, the possible outcomes are head head, head tail, tail head, tail tail. So 4 possible outcomes are there. So sample space is the collection of all possible outcomes. Here it is generally notated by a set notation. All possible ordered outcomes. So an event is sorry an event is a subset of sample space. So 2 examples are considered here. The example 1, in a tossing a coin twice, what is the probability of getting 2 heads is called one subset, one event. Example 2, in the same example, it is tossing a coin twice, getting head first is again a sub-event. So likewise, we can consider a good number of examples for taking this sample space. All possible outcomes are considered in sample space. So generally, two good definitions which are very much required for stochastic processing as well as for a communication engineer. The first term is mutually exclusive. That is, if the two events does not occur at the same time, then we can say it is mutually exclusive events. So if we consider A and B two events, if P of A intersection B is generally the joint occurrence, P of A intersection B is the joint occurrence of event A and B, which is 0. That you mean by the mutually exclusive events. So one more parameter is that statistically independent. If A and B events are there, the joint occurrence of events A and B is equal to the multiplication of individual probabilities is the condition for statistically independent. If A and B are statistically independent, P of A intersection B is equal to P of A multiplied by P of B. Now, the important definition comes into picture in stochastic processing or random processing. The first one is random variable. Random variable is a mathematical function that maps all elements of sample space into the point on the real axis. We will see with considering one or two examples. So consider a random experiment of tossing a coin twice. So sample space is just previously discussed: head, 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 tail, tail, head, tail, tail. Now, here a random variable is defined as the number of heads in the experiment. So x of tt is, because no head, 0. X of h comma t, 1 head is equal to 1. X of t comma h, 1 head is equal to 1. X of head comma head, 2 heads is equal to 0. This is a process of mapping all possible outcomes onto the real axis is called a random variable. Random variable means it's not a variable. It's a function of sample space. Mapping of all possible outcomes mentioned in the sample space are mapped onto the real axis. So a similar example, one more example, rolling a die. The possible outcomes are 1, 2, 3, 4, 5. Now we can define a simple random variable. X of j is equal to j. J is lies between 1 to 6. Now, after definition of random variable, two important parameters that define the behavior of the random variable, that are cumulative distribution function, probability density function. And random variable may be a continuous random variable, a discrete random variable. So first here, the probability density function is called generally probability mass function in case of a discrete random variable. For each xi event, the probability will be mentioned here. P of xi is equal to Px is equal to xi. So always it's a golden standard. That is, the probability of occurrence of any event is always lies between 0 and 1. If you add all the probabilities, it is always equal to 1. So in this, suppose previously we had taken tossing a coin, 3. Now number of heads in a tossing 3 coins, 0. The probability is 1 by 8, 1, but the probability 3 by 8, 2 with the 3 by 8, 3 with 1 by 8. Xi indicating the number of heads in tossing a 3 coins, which can be easily calculated by means of experiment. So just now I have mentioned the two important parameters that define the behavior of random variables is cumulative distribution function. For a continuous random variable, it is defined as capital Fx of x is equal to P of x less than or equal to x. And the important point to be considered is that the properties of cumulative distribution function. That is, first one is capital Fx of minus infinity is equal to 0. If you substitute this in this equation, Fx of minus infinity is equal to probability x less than or equal to minus infinity. Less than minus infinity, nothing exists. So we will say that its value is 0. Second property is that Fx of infinity is equal to 1. That is, if you again substitute in this formula, capital Fx of infinity is equal to probability x less than or equal to infinity. So all the things happens from minus infinity to plus infinity. So less than infinity means all possible events, all possible outcomes exist in that region. So sum of all probabilities is always 1. So Fx of infinity is equal to 1. So the third property is just a conclusion of first and second. It's always a probability lies between 0 and 1. Fourth property is that Fx of x1 less than or equal to Fx of x2 if x1 less than x2, indicating that the cumulative distribution function is always monotonically increasing function. It should be always monotonically increasing function, and it should always ends with 1. The CDF function ends finally with 1. And fifth property is a calculation of probability that x lies between x1 and x2, just Fx of x2 minus Fx of x1. These are the properties of cumulative distribution function. These are very much required for a communication engineer while characterizing the noise added to the signal. In general, we will consider for a wireless communication system or a wired communication system, we assume that noise having the characteristics of Gaussian density function or a Gaussian distribution function. Coming slides, it will be there. So the next one is probability density function. The next one is probability density function. That is, it is denoted by small fx of x is equal to dfx of x by dx. That is, differentiation of cumulative distribution function gives the probability density function. And the properties of PDF, the probability density function, is that it's always 0 less than or equal to fx of x for all x. And the area under the probability density function is unity. The area under the probability density function is unity. And by virtue of this property, that is, PDF is differentiation of CDF. In continuation, CDF is integration of PDF. So here the formula is mentioned here, minus infinity to zeta fx of zeta d zeta. Similarly, the fourth property. So the properties of PDF and CDF are very much required to some solving the problems of the random variables. The next one is some important density functions and distribution functions generally used in wireless communication systems. And not even in wireless communication system, it has a good number of applications in all science and engineering applications. All science and engineering applications. So the fx of x is the probability density function of Gaussian function. Fx of x is equal to 1 by under root of 2 pi sigma x square. Sigma x square is a variance of random variable. We will define these parameters in the next sessions. E power x minus mx whole square. Mx is called the mean of the random variable x by 2 sigma x square. So you can see here the shape of the Gaussian density function and the Gaussian distribution function. Remember that the area under this Gaussian probability density function is 1, and fx of x starting at 0, ending at 1, and monotonically increasing function. You can observe this in every CDF. And binomial PDF and CDF. This is a discrete random variable. It's a discrete random variable with probability density function is mentioned here. With the probability density function, it's a impulse function with the changing amplitudes. And see here CDF. CDF is a staircase function. It's a u of x unit step function, addition of unit step functions, and it's a monotonically increasing function ending at capital 1, starting at 0, ending at 1, and monotonically increasing function. Every discrete random variable will looks like this only. It's a staircase function. Fx of x will be a staircase function. So this is again one more example of discrete random variable, Poisson distribution. Its probability density function is shown here, and its CDF is shown here. CDF, the cumulative distribution function, is a staircase function. So always starts at 0, ends at 1. And one more general uniform distribution, which is again generally used in what I can say the quantization used in digital communication system. Quantization noise can be modeled as a uniform distribution. You can see here the area under this uniform distribution function is unity, and you can see here the CDF of uniform distribution having a slope of line starting at 0, ending at 1. So this is all about the discussion of definition of probability. What do you mean by sample space? What do you mean by random variable? Definition and properties of cumulative distribution function, probability density function, and the waveforms and equations showing some important PDFs and CDFs. All these PDFs and CDFs are generally considered in modeling of noise in wireless communication systems. So exponential distribution, one more example, exponential distribution, its corresponding PDF and CDF. So at the end of unit 1, that is week 1 lecture, I will show you the applications of random variables in communication system. Thank you. One and all will continue in the next session.